Oil makes up the largest portion of our energy use, so oil alternatives were the place to start. For 30 years, the U.S. has been the leading producer of biofuels.
Hey, Scott.
Hey.
You ready to take a ride?
You betcha. What do you got here?
Well, it's my secret. We're going to tie it on the tractor, and we're going to go out, and I'll show you what we're going to do with it.
You got me a little worried.
Yeah, let's put it on the bucket.
All right.
Now, up a little bit. There you go. All right, let's get on.
All right.
We'll go. I'm going to let you drive.
Let's do it. Oh, good.
Yeah, I'm serious. Yeah.
We may never get there.
Crank it up.
Watch your dog.
Yeah.
Good? How many gears does this have?
About, I don't know, 16?
Oh, good.
I think biofuels, it's the easiest thing to do because it's most similar to petroleum.
We're used to it.
And put in combustion engines, so we don't need that many changes. The United States has used corn, but the problem is you got this big, huge plant, and all you're using are those little tiny corn kernels.
So you're actually just using the food.
It doesn't make sense in many ways. You know, not only is it competing with food, which, you know, raises some moral questions, but it tends to be much more energy intensive than other ways of growing biomass. It tends to have a much larger carbon footprint, and it uses much more resources, fertilizer, and other stuff.
Okay.
So ideally, we want to move to a next generation of biomass material.
In Louisiana, they're already growing this next generation of crops. But will they be a better feedstock than corn?
Boy, this is an amazing root system.
To give an idea how tall it actually is, this is a 20-foot pole. The other day I measured, it was 18 feet.
Now, how long have these been growing?
Well, they were planted in May, middle of May.
Of which year?
This year.
May of this year?
Yeah, this is Jack and the Beanstalk territory here.
And we're in September now.
Yes.
Now, what is it? I mean, what are we looking at?
Well, it's a hybrid sorghum. It's bred especially to make cellulose.
Okay.
And the cellulose is going to be broken down into making ethanol.
If we look to the future of biofuels, we need to use better feedstocks.
Right.
We should not, in my opinion, be using a lot of food to produce fuel.
Yeah.
Right? And so we need to learn how to turn lignocellulose material, the structural material of plants, into fuel.
So the actual stalk.
The stalk, the leaves, some of the roots, and so on.
Right. It seems cellulosic crops can be very productive on farmland and in a warm climate. But what about where conditions aren't so ideal?
New York State is not a corn-producing state. We can produce trees quite well, and we grow a lot of the perennial grasses quite well. So if you're looking for a national initiative on biofuels, you need to be looking at feedstock availability across the country, not just what we have in the Midwest or the Southeast, but how all parts of the country can play in this initiative.
Mm-hmm. Can I pull one?
Oh, yeah.
Is that all right?
Yeah.
Is it pullable?
They're pretty
Oops.
tough.
Broke off.
Yeah.
Switchgrass is just one of a number of perennial grasses that we can grow in agriculture across the country. And so why not look at different possibilities?
So you're saying these kinds of grasses can be grown in places that just don't make sense for food crops?
What we typically call marginal land. And
Okay.
we've got no shortage of marginal land in this area, which is why you see the changes in agriculture that we've seen from a lot of small dairies over the years to a lot of land that's just sitting idle.
So far, cellulosic crops look good. High yield per acre, on marginal land, and in different climates. But what about turning them into fuel?
What we do in this laboratory is very much about microbiology, using microbes to do the conversion of sugars into biofuels.
So there's sugars in this fibrous cellulosic stuff,
Yes,
and you're trying to liberate it.
exactly.
Okay.
Okay. The challenge, though, is how do you liberate those sugars in a very cost-effective way? Now, I can look to you dead in the eye today and tell you we can make ethanol from cellulosic material. It's a no-brainer. We know how to do that. I can't tell you for sure that we can do it economically. It's one thing for me to say I can do great things here in the laboratory with my reactors.
I've gone from this to that.
Exactly, but it's another issue to really scale this up into hundreds of thousands of gallons, millions of gallons.
Yes.
So now there are some demonstration scale facilities, you know, a few million gallons a year, 10 million, 15 million gallon a year facilities. You know, pretty, in an energy sense, very small.
Right.
You know, we're talking now, I think this year the US produced 25 million, 30 million gallons of ethanol from cellulose.
Okay.
You know, compared to 10 billion
Right.
of the corn ethanol.
If I'm hearing you right, Dan, one of the great challenges then, as with most things energy, is scale. Just the scale of taking a low density fuel, a crop, and converting it into a high density liquid.
You know, for bioenergy, scale is exactly the challenge, is exactly the problem. And because we use so much energy, it's mind-boggling how much energy we use. And if you make it from biomass materials, from land, you just need huge amounts of land.
Right.
I think in the end, we, the world, are going to decide that biofuels are a good option.
Okay.
But we'll never see biomass replace petroleum. It'll never happen.
Right. If biofuels won't replace a large percentage of oil, what will? Some say compressed natural gas, or CNG.
This is natural gas, just like you burning your stove at home.
Okay.
Except we're going to run it through a compressor and pump it up to 3,800 pounds and then put it in the bus.
3,800 pounds is a lot.
Hell yeah. But that's the only way you can get that much gas into such a small area.
So there's a big engine sitting in the back?
Yeah, yeah.
Is it different from a diesel engine?
If you look at it, you wouldn't notice the difference. It looks just like an engine.
Same thing,
Just like
just a different fuel.
There you go. That's as simple as it gets, just like on the bus.
Is this the tailpipe?
That's the muffler and tailpipe. And,
So I'm standing right here next to the emission.
oh yeah.
Is that hurting me?
No, no.
What's coming out of there?
The emissions on these things are very low. As you can see, it's very clean. There's no smoke coming out.
Yeah.
So
I mean, on a diesel, we'd be seeing.
Oh yeah. Well, you know, in the cleaner diesels, it's not as bad as the old smoke going out the tailpipe.
Yeah.
But still, this stuff you never see it unless something's drastically wrong. You'll never see anything come out of these tailpipes.
I mean, we're in a room.
It isn't just a perception. It actually is very clean fuel. And when it burns, you just get carbon dioxide and water vapor, and that's pretty much it. You don't have all the smoke and particulates that you see in diesel. So it's a very clean burning energy source, and more transit systems are looking to get into it.
So looking at the whole system you've got here, and you've transitioned from fully diesel just over 20 years ago to now fully CNG.
Yes.
Compare that cost-wise and some of the pros and cons of making that change.
The actual cost of the fuel is less than diesel, and has been for the last several years. Natural gas is cheaper per mile to operate these buses than diesel. But the biggest issue is the cost of getting into it. You have to have compressors to compress the gas. So we have 5 really big compressors that are running all the time.
What happens is you have a higher capital cost, but you have lower energy costs.
Right.
So if you use the vehicle a lot, then you end up making it very attractive economically. Natural gas could be used in heavy-duty vehicles, in buses and trucks, that are fleets, and you have central stations.
So you get your compression done centrally,
Yeah.
and you're sending them out from, like the bus station that we visit.
Like a bus station works very well.
If you took all of America's city bus fleets and made them all compressed natural gas, it wouldn't have that much of an effect. It's such a small percentage of the total diesel that's burned in America.
Really?
Yeah, the city buses.
Yeah.
But a lot of trucks out there do also. Think of that. The over-the-road trucks, the city trucks, all the delivery trucks, okay? If you took all of those vehicles and converted them to compressed natural gas, which they could be because they're fleets,
Right.
you would have an impact.
Like biofuels, CNG will be a valuable supplement, but it won't replace oil. Meanwhile, demand for oil keeps growing, and a lot of people are worried we're running out. I went to see the Canadian oil sands, where plants like this could power 340,000 people per year.
Oil sands, if you could see it in the reservoir at the temperature it's at there and the depth, it's like a hockey puck. It's that hard.
So it makes it hard to get out.
It does. And where it's very shallow, it has been mined, but 80% of the oil sands needs to be recovered by thermal or steam methods. In the steam plant, we're using natural gas. Think of it as a big kettle.
So natural gas is being burned, boiling some big boilers.
They keep feeding water in,
All right.
keep taking steam off. So we pump steam in the injection well, you melt the oil out of the rock, and you end up with hot water and oil mixture coming back. Oil and water comes into this building where there's multi-stage separation process to take the oil from being at about 70% water.
Okay.
And when it leaves here, the oil has to be less than 0.5% water. I like to think of this as a heavy oil or oil sands facility, but we're primarily a water plant. To be good at this, you need to be good at recycling and treating and cleaning water.
Compared to the days of the large oil fields in the Middle East, yes, it is relatively expensive. It takes about $60 to $70 intermediate crude price for the oil sands to be economically competitive.
If you just consider resources that you might be able to get at for costs of less than, say, $70 a barrel, then we've got about another 4 trillion barrels of oil left in the ground to get out.
4 trillion barrels.
4 trillion. And between now and 2030, we'll use maybe 1 trillion barrels of oil at most.
Once was a hockey puck, and after this building, it looks like this. Amazing.
Like any natural resource, how much oil there is to get out of the ground depends really on how much you're willing to pay for it.
Yep.
And as the price of oil goes up, people are willing to go after more difficult resources.
So we're not running out. As price climbs, so will supply. It looks like the main replacement for oil will be different sources of oil. And as long as we have cars that run on it, we'll be dependent on it.
We've had these petroleum-based vehicles for 100 years, and we are starting this transition away from it. And the transition is towards electric drive vehicles, meaning vehicles that are propelled with an electric motor instead of a combustion engine. And so with hybrid vehicles, we're gradually shifting the balance between the gasoline and the electricity. We're increasing the electricity and reducing the gasoline.
You're weaning us.
We're weaning, yes, we're weaning ourselves off of oil slowly. We sometimes refer to a regular hybrid as really a gasoline-electric hybrid, meaning all of the energy comes from the gasoline. With a plug-in hybrid, now you get some of the electricity from the grid, from a plug. The way you do that is you put a bigger battery in that will hold more of the electricity, and therefore you can replace more of the gasoline. So basically what the difference is that you can run the vehicle in an all-electric mode more of the time. Electric motors are so efficient that the more you can use the electric motor, the better you are in terms of reducing energy consumption, carbon.
Why not just jump to electric?
The reason we're not going there fast is because the batteries are expensive.
Okay.
It's a big challenge today. We don't have the batteries at the appropriate cost and weight to compete with the range of our home, our personal auto, etc. But
they're just too heavy.
And expensive.
So how expensive are we talking? If I had an unlimited car budget, could I get an electric car that will do everything a gasoline car can do?
Wow. Nice design.
How many batteries do you think are in this thing? There's almost 7,000
You got
batteries.
me.
Almost 7,000 batteries.
And they're all the new...
Yeah, as a matter of fact, they just look like this. Types that you'd see in your laptop.
7,000.
Right now, we're talking, let's say, there's a 244-mile range on these.
Is that what the range?
It's about the range.
With some
Assuming you
mix
drive
of
conservatively.
Highway and
city, correct.
That's pretty...
Yeah, and then you've got the performance mode.
I'm guessing this thing isn't cheap.
You know, base price starts off at $109,000,
Okay.
and that doesn't include options.
On the other hand, we should not ignore the advantages of electrification. First of all, it's a pretty good performance vehicle. If you want torque,
Yeah.
get a battery.
Now, the standard model is going to take you from 0 to 60 in 3.9 seconds.
3.9.
3.9 seconds. The sports model is going to take
Wear
you
your
from
helmet.
0 to 60 in 3.7 seconds. There she is in all her glory, being charged up.
You drive a Tesla, right?
I do. I do sometimes.
I mean, were we looking at the future there?
Well, I think the important thing about the Tesla and the electric vehicle front, because you know it's an expensive sports car with limited utility because it's a sports car. But the importance of the Tesla in the electric car movement is that it demonstrates one key aspect of electric car introduction, and it's a very basic aspect: fun.
Whoa! That's fast. Woo!
0 to 60 in 3.7 seconds? No noise, no transmission, no gas stations? This car isn't just as good as a regular sports car, it is better. If I had an unlimited car budget, I'd be driving this one home.
We will see a gradual electrification, really the pace being driven by advances in battery technology more than anything else.
Okay.
But most importantly, if we're not going to get any of our transportation energy from oil, we're going to have to get it from somewhere else. And so where are you going to get the extra electricity to run all those electric cars?
Right.
When you go through the numbers, it's a non-trivial 25, 30, 40% more electricity we have to generate.
Yeah, that's a huge number.
Right.
Wow. I went to look at transportation, and it pointed me back to electricity. Where are we going to get 40% more power? Coal? Or can we successfully switch to an alternative? Iceland sits on a geologic hotspot, allowing them to get half their energy from geothermal.
Just briefly, what's going on beneath us?
So basically, we are on the seafloor. The sea level is 10 meters below us. That sea water is heated up by steam,
How hot?
200 degrees centigrade.
And it's those very hot waters that we tap and bring to the surface to create steam to feed into the geothermal power plant.
Right.
Boy, it's a natural.
It's quite simple.
What are we seeing here?
This is the actual well tub from a geothermal well. And as you can see, the pipes channel water and steam from these wells to feed the power plant. You just drill the well, you look at it for a couple of weeks, see what you get out of it, and then it just flows.
These wells feed steam to the Hellas Heady plant, which could power 90,000 people per year.
So this is the turbine.
This one,
Looks like a giant jet engine.
it works completely the same, but the other way around.
So where's the generator?
Generator's over there.
Okay, so this is where the electricity gets made. And it's remarkably clean.
Yeah.
Do you have any chemicals in this operation?
No, none at all.
Just the steam and the water.
Water and steam.
Unbelievable. What do I do with it?
Well, you put it on your face.
On my face. So this is natural.
This is natural. Yeah, this is just silica precipitate from
You're going for the whole thing.
from the geothermal line.
Woo!
It sort of goes under your top layer of the skin, I understand. And
Is that right?
yeah, sort of
Silica is
release-
a good abrasive, that's for sure.
abrasive, yeah.
So it
use it
exfoliates
also-
you.
Exfoliates.
I can't wait for my people who used to be my friends to see this.
The most amazing thing about the Blue Lagoon is that all the hot water in the spa, and even the white mud that it's famous for, comes straight out of the Svartsengi power plant.
I think every 75 megawatt power plant in the world should have a Blue Lagoon right next to it.
I totally agree with you.
But geothermal energy this powerful is dependent on the geology.
California has we have the geysers,
Yeah.
and Iceland runs on geothermal,
Yeah.
but those are places where the Earth concentrates the geothermal energy into small locations. When you do that, it's really worth doing. But the average geothermal has a power density that's 10,000 times less than the solar energy.
So geothermal is regional, but the sun is nearly everywhere. Could solar be the answer? REC Solar is the largest residential installer in America.
People still don't know much about solar. It's changing, but it's still a relatively new technology, which really came about with having more popularity during the last 3-4 years.
How much of a homeowner's decision to install solar is based on philosophical or passion versus economics?
Most decision makers actually go for the economic reason. I would say 80%, 20% environmental reasons. Here in a neighborhood like this, you would get an incentive from the utility, and in addition, you get a federal investment tax credit.
Sure.
Typically, what a homeowner can achieve here is probably an 8 to 10 year payback.
The average solar array powers just 0.4 people per year, which means it'll take several years for the savings to offset the cost of the panels. Is it 10 to 20 years, 30 years?
It depends on what you pay for electricity today.
Yeah,
You know,
all relative, isn't
if you're, you know, in Palo Alto in the middle of the afternoon, your photovoltaic, you know, it's cost effective. You know, if you were in Hawaii, you know, where they have a very high cost of electricity, it could be cost effective today. On the other hand, if you have coal-based electricity right now, you know, that you're paying, you know, 4 or 5 cents a kilowatt hour, it may never be, you know, really competitive. So there's not a simple answer, but in the right place, it's here today.
Turns out solar too is regional. It's affordable where sun, subsidies, and electric prices are high. But where we have all these things, can we turn solar panels into a solar power plant? I went down the road to the Diablo Valley College.
Basically, it's a parking lot canopy that provides shaded parking, but there's solar on the rooftops. So the solar produces about 50% of the campus's peak electrical demand.
Why in a parking lot? I mean, usually we see these panels up on a roof.
What we found is that if you can build a solar parking shade structure in, you know, a wide open parking lot that has lots of available space, you can actually drive the economics down much better than you can on the rooftops.
So how does a community college or an educational campus afford the front-end cost of something like this?
Well, most of them don't have to worry about the upfront cost. The campus would basically enter into a long-term power purchase agreement at a rate that is less than what they're buying from the local utility. So they're getting those savings from day one.
And they enter into that agreement with the utility?
No, they would enter that into with a financial institution that would actually own the asset.
Okay.
Okay, so say a bank would own the asset, and then we would design the project, build the project, do the operation and maintenance of it on behalf of the bank, which is selling the power to the campus for, say, 20 years. And that's where the savings get generated.
So that's a neat combination of partnerships that are going on there.
Yeah, it's a great example of public-private partnership to benefit the mission of a college campus.
With creative financing and in the right places, solar plants are a workable solution. But they're still limited by high price and low output. This one could power just 200 people per year. They're using a different technology to get more out of solar plants in Spain, like at Solarcar, which could power 1,200 people per year.
We have a huge field of mirrors, and they are continuously moving in order to track the sun and to concentrate solar radiation on the top of the tower. And we generate steam that we drive to the steam turbine in order to generate electricity.
The plants are larger and therefore more efficient. The footprint is smaller as well. And as you use the heat to produce energy, the plants have what we call thermal inertia. So they don't go on and off the grid. when the solar resource disappears. So we can provide utilities or grids a more stable production.
When we were leaving Solarcar, we saw this beautiful image. The light beams were converging right in front of the tower.
When you don't have a very good day, it's sort of cloudy, what they do is they take out part of the solar field and they put it in what they call the waiting point in front of the receiver. People always love that. The people who are operating the plant, they don't like it because it's a sign that they are not able to produce as much as they could.
At 16,000 people per year, Andasol uses hundreds of mirrored troughs to turn heat into power.
Oh, that's very warm. I can feel it here.
Yeah.
It's like, woo, it's hot. Right here? Yeah. Woo.
The heat makes steam to turn a generator or is stored in tanks of molten salt to be used later in the day. So you're storing heat, not electrons, with concentrated solar.
Yeah. Storing electricity today is not efficient. There are no known technologies cheap enough, let's say, while storing heat is something used in other industries.
But on the day I was there, the troughs never swung upward to gather heat. This plant also never got out of the holding position.
For the large utility scale solar thermal plants, you know, they have to be in places that have very clear, direct sunshine, not kind of, you know, reflected stuff, which you can get away with more easily with photovoltaics.
Obviously, there's a big room for improvement, and we just got started. Technologies are very young. You are seeing technologies for which there are, in the case of a tower, 2 towers worldwide. In the case of troughs, a bunch of them worldwide. So there's a huge path that we will go through in order to reduce the cost of these technologies and improve efficiency.
As promising as this technology appears, it's probably decades away from being an affordable solution. We'll need some other alternative to provide large-scale power. For 40 years, Denmark has led the world in wind, which now makes up 20% of their electricity.
Welcome to turbine number 4. Coming in. So what I'm going to do now is to press the stop button. You can have the responsibility.
Absolutely. Stopping the turbine. Oh, I can hear it. It just grinds down very quickly.
Yeah.
Just a few seconds.
Let's climb to the top.
How high are we going?
It's 50 meters.
How narrow do we get at the top?
Oh, like 1.5 meter.
Okay. All right.
Okay. One important thing is use your legs.
The benefits of wind are many. It produces a lot of power.
Right.
It's fast to install and scalable in size. It does not produce CO2 while producing power. To Denmark, it's also a big export commodity. So for us, there's some additional benefits.
Sure.
In Denmark, we sort of invented the modern turbine. It was built by a combination of hardworking entrepreneurs and some visionary politicians who could see this already in the beginning, 20, 30 years ago. And of course, the consumers, me, and at that time my parents, I guess, they had to pay the price for wind energy.
Right.
So for a while, you could say we were, other things being equal, paying more than we could have done, but to build up this industry and to make sure that in the future, Denmark would reduce its dependency on imported energy.
We went from 0% of wind penetration to 20% or 22% as we're approaching now. Slowly but surely. It has been a long but concerted effort. Every year, one bit at a time.
Whoa. Woo.
You like the view? Awesome. It's a well-known Danish concept for wind turbines.
Right.
Which is just to use standard, simple components, almost taken from the shelf.
Sure.
It takes care of itself This fellow works for 20 years or more.
Very reliable. Pretty simple
reliable.
components.
Very simple, yeah. Keep it simple.
The 3-blade turbine we see around the world was pioneered and perfected here. They can be built in months and rolled out in any number. But the turbine is only part of the equation. The rest is the wind.
And of course, when the wind does not blow, we generate nothing. That we guarantee.
One of the problems with wind is its intermittency. The wind doesn't blow all the time, and so you don't get the electricity from wind all the time. And again, because it's hard to store electricity, you need to figure out how to handle that intermittency.
The main idea is a combination of different technologies, diversification. That's what we have done in Denmark. We have our combined heat and power plants that are stable, baseload, and then we have our strong interconnectors to the other countries.
Okay.
That's crucial. You cannot do this without being able to exchange large amounts of electricity across borders.
Exactly.
Denmark has made this intermittent resource a success. But this is a country of only 5 million people. All their turbines combined would power just 340,000 people per year. Can we do the same thing in a much larger country?
But this sort of shows you in Texas what's going on, so you get a relative sense of where you are.
Yeah.
Which means as soon as you take off, you're flying over 25% of U.S. wind energy capacity is here. Basically, half of U.S. wind is probably within 500 miles of here.
Let's do it.
I'm ready.
We've got almost 100,000 acres in the Roscoe Wind Farm.
100,000 acres.
And about 400 landowners. And this amazing wind resource that we've got through here.
Did you ever think you'd be using the word amazing wind?
We've cussed this wind all our life. It destroys our crops. We have sandstorms. It blows our soil away. And you talk about an attitude adjustment. Now we've had it 180-degree attitude adjustment relating to the wind. It's just been phenomenal.
You really led this thing in many ways, and I know you're a modest person, but 4 or 5 years ago, if I was standing right here with you, we'd be looking at farmland and ranch land.
The more I learned about the wind industry, the more I believed that we had the combination that we needed to build a wind farm here. It just, somebody just needed to do it.
And this is a community that's welcoming this with open arms.
Yes.
Nobody's saying, hey, not here in my backyard, not on my farm.
No. West Texas is an agriculturally depressed area. It's just an economically depressed area.
Yeah.
And we've just had to sit here and take what Mother Nature brings to us in the way of rainfall and try to make a living on this country. And it's gotten so tough that our young people don't come back. But now, with our windmills and our opportunities here that it's bringing, it's turned our communities around. We've got, for the first time ever, these landlords have an opportunity to receive a regular paycheck.
For the farmers around Sweetwater, wind turbines are a beautiful thing, and I would tend to agree. But to get 20% of U.S. electricity from wind would require another 200,000 of them. We could do that, but people may not want to look at that many turbines.
Wind power is best in windy areas, but people don't tend to live there. And so we need to get the electrical grid out to the wind farms in order to be able to bring that electricity into the cities.
We found the best wind areas, and then we came up with a plan to build transmission out to those areas and deliver it back in to Dallas-Fort Worth, Austin, San Antonio, and Houston.
Okay.
That plan is 2,300 miles of high-capacity transmission. It's about $5 billion, and we're going to have it completed by the end of 2013.
What would it take to do that nationally? Just scale it up for me a little bit.
Well, there are two debates on this. Okay. One is who pays for it. So would we encourage at the federal level a payment system like we have today, which is everybody pays, which is different from the way the rest of the country does. And then there's the siting issue. Nobody wants to have transmission lines running through their 100-year-old family ranch.
Right.
It's never been the case. This is going to be the challenge if the federal government says, okay, we're going to do that. We're going to site these lines. Are they really willing to get down and go property by property with county judges, county commissioners, and landowners in siting these lines? Because that's what's required.
Right.
So to make wind work on a grand scale, we'll first need to figure out transmission, and then how to manage that much intermittent power.